Hi, my name is Nuala Caffrey, and the title of my talk is The Ultimate Memory, so that's computer memory. Or the main title of my thesis is Spin Transport in Multifurrowick Tunnel Junctions. And I work in the computational spintronics group. So, one of the most important components in any modern computer or iPod or digital camera is its memory. And there's a huge section of the electronics industry devoted just to making computer memories faster and cheaper and just more efficient. So the way, when you save something on your computer, it's encoded as strings of zeros and ones. And how does this work physically inside your computer? Well, there are lots of little magnets, and using a magnetic field, you can force the magnetization to a line, either pointing up, which would be 0, or down, which is 1. That's ferromagnetic memory, but you can also have a different type of memory called ferroelectric memory. So instead of using a magnetic field, you use an electric field to force the atoms to point in, again, one of two different directions. So that gives you two more states. But both of these different types of memory have advantages and disadvantages. And one way to combine the advantages while eliminating some of the disadvantages is just to combine the two into one ultimate memory device. And this is what multifurrowick memory is. So how does that work? How do you combine the two? Well, there are two different ways. You can have single phase. This is where you take one material that both has the ferromagnetic memory and the ferroelectric memory. But there are problems in that they're very rare in nature, and those that do exist only work at extremely low temperatures. So you'd have to put your iPod into a vat of liquid nitrogen or liquid helium, which isn't very practical. So instead, you can take the ferromagnetic memory part, the ferroelectric memory part, like here, and just stack them on top of one another. And this, again, has the advantage that it's easier to model, and that's important because that's what I do. I work in computational physics. So there's a precise mathematical formulas that describe how these materials work, but they are ridiculously complicated to solve using pen and paper. So instead, we numerically solve the equations on a computer. And this is what I use density functional theory to solve these equations. And using that, I can calculate the properties of this material. So does it work? So I need to be able to differentiate these four states, the 0, 1, 2, and 3. And the answer, well, these are the four states. So the current flows through them. And in the first one, the 0, the two magnetizations point in the same direction. For number 1, they point in opposite directions. But now we can include these black arrows. And they can either point to the left or the right. So you can see that there are four different states. So I calculate the current flowing through them. And if the current flowing through all of them is the same, then the device would be useless because I couldn't tell them apart. But it turns out, due to the complicated process of quantum mechanical tunneling, that I can tell them apart. And so it looks like it should work. So in the future, when you buy your iPod or your digital camera, I hope there'll be a sticker on it saying that there's multifurrowick memory inside. And I hope that when that happens, you'll at least somewhat understand what that means. Thank you.